Today we will start our lecture on a very important topic called buoyancy from the subject of fluid mechanics. So we will start our lecture. So what exactly buoyancy is? When a body is immersed in a fluid, like when you try to dip any object in water, sometimes you will see that an upward force is being applied by the fluid on the body. That upward force is called the buoyant force, or simply the buoyancy. So we like explained here, when a body is immersed in a fluid, like you immerse some object in the fluid, an upward force is exerted by the fluid on the body. So there is an upward force that is being exerted on the fluid on the body. This upward force is equal to the weight of the fluid displaced by the body. Like if the body's weight is more than the weight of the displaced liquid, then the body will not float, it will simply sink. So for a body to float, its weight should be equal to the volume, to the weight of the fluid displaced by the body. If it is the weight of the body is less, then it's perfect. If it is equal, still it will float. But if the body's weight is more than the weight of the fluid displaced by the body, then the body will sink. So this upward force is called the force of buoyancy, or simply the buoyancy. So who has provided the concept of buoyancy force? It was provided by the Archimedes, and then the calculations of the buoyancy forces are done by the principles of Archimedes. So now in the next section we will calculate the forces of buoyancy. So now we will study that how we will use the principle of Archimedes to calculate the buoyancy force. Here you can see that we have considered an element that is below the free surface. So this is basically our free surface, and there is an element, right? So the upper cross-sectional area, which is denoted by point M, this point is at a depth of h1, and this lower point, which is the point N, is at a depth of h2. So here we have considered that A is the cross-sectional area of the element and rho is the density of the fluid. So now we know that the force is pressure into area. So the force at this point, at the cross-sectional area M, will be pressure into area, which is P1 into A, and at point N will be pressure into area. In this case we consider it as a P2 into A. The pressure, we always know that the acts normally to the surface. So now by using the concept of hydrostatic pressure, we know that the hydrostatic pressure, this P1 is equal to rho g h1, and at point N it is P2 into rho g h2. So now we know that summation of, so if I just raise this part, if I say, just to make some space, we know that the summation of forces is equal to 0. That means the buoyant force is equal to the difference of the pressure force minus P1 dot A, or you can simply write it like this, P1 minus P2 into A. So, or now you can insert the values of pressure into rho g h2 minus rho g h1 into A, or you can simply write rho g A into h2 minus h1. So this is your buoyant force. So now I erase this section. So now you will notice that this term A into H2 minus H1, this is basically, this term is the volume of the cylindrical element that we have considered. So we can say that when the volume of cylinder, I will write it here, I will just remove it, raise it. So the volume of the cylinder A H2 minus H1 is equal to the volume of liquid displaced. So now we know that this volume of the cylinder is equal to the volume of the liquid displaced, like in the first section what we have studied about the buoyant force concept. So when we immerse the cylinder in the liquid, we know that the matter occupies space. So like when we dip something, we know that it will occupy some space. So when we immerse cylinder in the liquid, it will occupy space equal to the volume of the displaced liquid or fluid. So buoyant force is equal to rho g and this volume. So this is the, this part is the basically displaced volume of the fluid. So we revise it, that we just have said that this is the volume of the cylinder which we have dipped into our free surface, and we know that this is equal to the volume of the liquid displaced by the body. So we have just instead of this thing, we have inserted its value, and we said that the buoyant force is equal to rho g into the displaced volume of the fluid. So this is basically the buoyant force. So now we will study the concept of center of buoyancy, the point where the buoyancy force acts, is known as the center of buoyancy. And when we study the stability of the submerged body, then we will need the center of buoyancy and the center of gravity. So we know that the point where the buoyancy force acts is known as center of buoyancy. So now we would like to know also that what is the center of gravity. So in terms of center of gravity where the weight of the body acts is called the center of gravity. So let's say this is my free surface. So we have immersed a body in the free surface. The body is submerged in water. So now you see that there is a point G where the weight of the body acts. So it's the center of gravity where the weight of the body acts, and then there is a point B where the buoyancy force is acting. So now there are three possibilities where the center of buoyancy could be. Number one, at G. Number two, above G. Number three, below G. Right? So there are different conditions for equilibrium. So now we simply make some three. It will be basically the position of the center of gravity and center of buoyancy will tell us that the body is in stable equilibrium or not in the stable equilibrium. How? Let's say I show you stable equilibrium. So let's say if this is kind of a surface, and there is a ball here. If I try to roll the ball in this direction or in this direction or in this direction, like if I disturb this its position by applying some external force, what will happen? It will eventually get a stable equilibrium. It will come back to its original position. But now let's say if the shape is like this, and there is a ball here, this is an example of unstable equilibrium, right? So if I try to push the ball, or if I try to push the ball in this direction or in this direction, it will never come back to its original position. This is called the unstable equilibrium. And then neutral equilibrium. So neutral equilibrium is like if there is a flat surface, if I disturb its position from here to here, then it's again in an equilibrium position. So neutral equilibrium is always when B is at G, like when the Buoyancy force and the center of gravity is exactly at the same point, both the points are at the same location. So then this is called the neutral equilibrium. So now we will study the stability of the body in the next section of the video. So now we will study the stability of the immersed body. So here in this case, now this is the first case when G is above B. So now the center of gravity is above the center of buoyancy. This is case 1. So now this is free surface and body is immersed. So now I try to disturb the body by applying some external force, and we'll see whether the body is in stable equilibrium or not stable equilibrium. Let's say I push the body like in this direction, and now this is the center of gravity and this is the buoyant force. So this is basically the weight of the body acting, and this is the buoyant force is acting. So I disturb the body in this direction, and now the couple which is being this force G is in this direction and buoyant force is in this direction. So it will also try to rotate the body in the same direction. So the external force and the couple that has been generated is also both are in the same direction. So what will happen? This body will not come into its original shape or original position, not the shape, the position. So this is called the unstable equilibrium. When G is above B, this is the case of unstable equilibrium. So now let's say in same situation, if I say B is above G, so now this is my B and this is my G, right? So let's say I have again disturbed the body in this direction. What will happen now? So this is my point of buoyant force. So buoyant force will act always in upward direction and the weight always acts downward direction. Now the couple will be, so this is your buoyant force and this is your G force. So they will try to revolve in the opposite direction. So now the generated couple will be against the external moment, like external force which we have applied in this, like in clockwise direction, and now the reaction force is in the anti-clockwise direction, and then this body will gain its original position. Like if we remove the external force, then it will come into back to its original position. So this is the case of stable equilibrium. So this is our case number 2. So now in case number 3, when the B and G are both at the same position, let's say let's say if a body is submerged here, and here is my B, and at the same point is my G at the same point. So what will happen if I try to apply an external force? Let's say body is in this direction. Now I apply a external force. So now up to the external force, at the same next new point, it will be again in the equilibrium position. So this is called the neutral equilibrium, that when you apply an external force, then the body again gains a equilibrium, but at the new position. So this is called the neutral equilibrium. Hope you have understood the concept of buoyancy, and in the next section, next video, inshallah, we will teach the numerical problems of the buoyancy concept. If you think you like the lecture and you have understood the concept, please subscribe my channel and like my video. Thanks a lot.